Hello, welcome to the fourth section of the course, Gaze-Based Control. In this section, we will begin with Ethan the Walker, where artificial intelligence and NavMesh will be added to our character Ethan. Then we will send Ethan wherever we like in Go Where I'm Looking. And finally, we will try to kill our character in If Looks Could Kill. Now we move on to the first video of the section, Ethan the Walker. In this video, we will make Ethan artificially intelligent, then we'll define NavMesh, then look at the random walker and get introduced to Unity programming, and then we will make script for random position and will finally make our character look like a zombie. We left off at the diorama, with Ethan hanging out. You can make him run around the scene if you have a keyboard or gamepad, but in today's VR, having that is not guaranteed. In fact, if you're viewing the scene with a Google Cardboard, it's pretty unlikely that you'll have a handheld controller. Perhaps there is another way to make him move around. One technique is to use the direction of your gaze while wearing your VR headset. To start, we want to replace the third-person controller prefab that we used initially with Unity's AI character, AI third-person controller, using these steps. Unity uses the word artificial intelligence loosely to mean script-driven, so let's begin. First, open the Unity project from the previous sections with the diorama scene and have the characters package imported from standard assets. In the project panel, open the standard assets third-person character prefabs folder and drag AI third-person controller into the scene. Name it Ethan. In the hierarchy panel, or in scene, select the previous third-person controller, the old Ethan. Then in the inspector panel's transform pane, choose the gear icon on the upper right of the transform pane and select Copy Component. Select the new Ethan object from the hierarchy panel or scene. Then, the inspectors panel's transform pane, choose the gear icon and select Paste Component Values. Now you can delete the old Ethan object by selecting it from the hierarchy panel, right-clicking to open Options and clicking on Delete. Note that this controller has a NavMesh agent component and an AI character control script. The NavMesh agent has parameters for how Ethan will move around the scene. The AI character control script takes a target object where Ethan will walk to. Let's populate that. First, add an empty game object to the hierarchy panel. Reset its transform values. Name the game object as WalkTarget. Then select Ethan and drag WalkTarget into the target property in the inspector panel's AI character control pane. At this point, we have an AI character in the scene, Ethan, an empty game object that will be used as a navigation target, WalkTarget, and we told the AI character controller to use this target object. When we run the game, wherever WalkTarget is, Ethan will go there, but not yet. The next header is NavMesh Bakery. Ethan cannot just go walking around without being told where he's allowed to roam. We need to define a NavMesh, a simplified geometrical plane that enables a character to plot its path around obstacles. Create a NavMesh by first identifying the static objects in the scene and then baking it. So, select each of the objects, the ground plane, the 3 cubes, and the sphere, and in its inspector panel, check off the static checkbox. You can do each object separately or Ctrl+click to select multiple items at once. Select the navigation panel. If it's not already a tab in your editor, open the navigation window from the main menu by navigating to Window, Navigation. Click on the Bake button at the bottom of the panel. The scene view should now show a blue overlay where the NavMesh is defined as shown. Let's test this out. Ensure that the game panel's Maximize on Play is deselected. Click on the Play Mode button, triangle at the top of the editor, in the hierarchy panel. Select the WalkTarget object and ensure that the Translate Game gizmo is active in the Scene panel. Now drag the red X and/or the blue Z arrow handles on the WalkTarget object to move it around the floor plane. As you do, Ethan should follow. Click on Play Again to stop play mode. Now we'll write a script that moves the WalkTarget object to random places. If you've done anything more than tinker with Unity, you've probably already written at least some scripts. We're going to use C# for the programming language. For this first script, we'll take it slow. We will attach the script to the WalkTarget object. For doing this, first select the WalkTarget object in the Hierarchy panel or the Scene view. In its Inspector panel, click on the Add Component button. Select New Script. Name it Random Position. Ensure that the C# language is selected. Click on Create and Add. This should create a script component on the WalkTarget object. Double-click on the Random Position script in the slot to the right of Script in the Inspector pane to open it in the MonoDevelop code editor. Let's quickly get introduced to Unity. Unity does a lot of things. It manages objects, renders them, animates them, calculates the physics of those objects, and so on. Unity itself is a program. It's made of code, probably a lot of good code written by some very smart people. This internal Unity code can be accessed by you, the game developer, through the Unity point-and-click editor interface that we've already been using. Within the Unity editor, scripts are manifested and configurable components. However, it's also made more directly accessible to you through the Unity Scripting API. API, short for Application Programming Interface, simply refers to the published software functions that you can access from your own scripts. Unity's API is very rich and nicely designed. That's one reason why people have written amazing plugin add-ons for Unity. There are many programming languages in the world. Unity has chosen to support the C# language from Microsoft, as well as a flavor of JavaScript which has its limitations. In Unity, script errors and warnings appear in the console panel of the editor, as well as in the bottom footer of the app window. The default script editor for Unity is an integrated development environment, or an IDE, called MonoDevelop. You can configure a different editor or an IDE if you want. C# scripts are text files that are named with a .cs extension. In a Unity C# script, some of the words and symbols are part of the C# language itself. Some come from Microsoft.NET framework, and others are provided by the Unity API. And then there's the code that you write. An empty default Unity C# script looks like this. Let's dissect it. The first two lines indicate that this script needs some other stuff to run. The using keyword belongs to the C# language. The line using Unity Engine says that we'll be using the Unity Engine API. The line using System Collections says that we also might use a library of functions named Collections to access lists of objects. In C#, each line of code ends with a semicolon. Double slashes indicate comments in the code, and anything from there to the end of that line will be ignored. The Unity script defines a class named Random Position. Classes are like code templates with their own properties, variables, and behavior functions. Classes derived from the mono-behavior base class are recognized by Unity and used when your game runs. The line public class, Random Position, mono-behavior basically says we are defining a new public class named Random Position, which inherits all the abilities of the mono-behavior Unity base class, including the capability of the start and update functions. The body of the class is enclosed in a pair of curly braces. When something is public, it can be seen by other code outside this specific script file. When it's private, it can only be referenced within this file. We want Unity to see the Random Position class. Classes define variables and functions. A variable holds data values of a specific type, such as float, int, boolean, game object, vector3, and so on. Functions implement logic, step-by-step instructions. Functions can receive arguments, variables enclosed in parentheses, used by its code, and can return new values when it's done. Numeric float constants, such as 5.0f, require an f at the end in C# to ensure that the data type is a simple floating point value and not a double precision floating point value. Unity will automatically call some special message functions if you've defined them. Start and update are two examples. Empty versions of these are provided in the default C# script. The data type in front of a function indicates the type of value returned. Start and update do not return values, so they're void. Each start function from all monobehavior scripts in your game are called before the gameplay begins. It's a good place for data initialization. All the update functions are called during each time slice or frame while the game is running. This is where most of the action lies. Once you've written or modified a script in mono-develop mode, save it. Then switch to the Unity editor window. Unity will automatically recognize the script as changed and will re-import it. If errors are found, it will report them right away in the console panel. This is just some cursory introduction to Unity programming. As we work through the projects in this course, I will explain additional bits as they are introduced. The random position script. Now, we want to move the WalkTarget object to a random location so that Ethan will head in that direction, wait for a few seconds, and move the WalkTarget object again. That way, he'll appear to be wandering around aimlessly. We can do this with a script. Rather than developing the script incrementally, I'm presenting the finished version first, and we'll go through it line by line. The randomPosition.cs script looks like this. This script defines a mono-behavior class named randomPosition. The first thing we do when defining the class is declare any variables that we'll be using. A variable is a placeholder for a value. The value can be initialized here or assigned elsewhere, just as long as it has a value before the script needs to use it. The meat of the script is the function named setRandomPosition. Let's see what that does. If you recall, the ground plane is 10 units square with the origin in the middle, so any xz location on the plane will be within the range from -5 to 5 along each axis. The line float_x equals random.range open parentheses -5.0f, 5.0f, close parentheses, semicolon, picks a random value within the given range and assigns it to a new float_x variable. We do the same thing to get a random z value. Usually, I discourage hard-coding constant values like this instead of using variables, but I'm keeping things simple for illustration purposes. The line debug.log prints the x and z values in the console panel when the game is running. It'll output something like x, z, 2.33 minus 4.02 because toString f2 says round up to 2 decimal places. Note that we're using plus signs to combine the parts of the output string together. We actually move the target to the given location with the line transform.position. We're setting the transform position of the object that this script is attached to. In Unity, values that have an x, y, and z are represented by the vector3 objects, so we create a new one with the x and z values that we generated. We give y equals 0 so that it sits on ground plane. Each monobehavior class has a built-in variable called this, which refers to the object that the script is attached to. That is when the script is a component of an object and appears in its inspector panel. The script can refer to its object as this. In fact, this is so obvious, if you want to call functions on the this object, you don't even need to say it. We could have said this.transformPosition equals, but the this object is implied and is normally omitted. On the other hand, if you had a variable for some other object, for example, game object that, then you'd need to say that when you set its position, like that.transform.position equals. The last mysterious bit is how we handle time delays in Unity. In our case, the transform position should get changed once every 5 seconds. It's solved in several parts. In the start function, there's the line start coroutine, reposition with delay. A coroutine is a piece of code that runs separately from the function from which it was called. So this line kicks off the reposition with delay function in a coroutine. Inside that, there's a while true loop, which, as you might guess, runs forever, as long as the game is running. It calls the setRandomPosition function, which actually repositions the object. Then, at the bottom of this loop, we do a yield return new, wait for seconds 5 sentence, which basically says to Unity, hey, go do what you want for 5 seconds and then come back here so that I can go through my loop again. For all of this to work, the reposition with delay coroutine must be declared as the IEnumerator type. This coroutine yield mechanism, although an advanced programming topic, is a common pattern in time-sliced programs such as Unity. Our script should be saved to a file named randomposition.cs. We are now good to go. In the Unity editor, click on Play. Ethan is running from one place to another like a madman. He waits for 5 seconds and again starts moving. Okay, that's pretty random. Let's adjust the NavMesh steering parameters to slow him down to a nice zombie-like pace. For that, perform these steps. Select Ethan in the Hierarchy panel. Navigate to Inspector, NavMesh Agent, Steering. Set the following: Speed 0.3, Angular Speed 60, Acceleration 2. Play again. He has slowed down, that's better. One more finishing touch. Let's turn him into a zombie. I have a texture image named ethanzombie.png that will help us perform these steps. From the Assets tab on the main menu, select Import New Asset. Navigate to the Files folder with the assets that come with this video. Select the ethanzombie.png file. Click on Import. For tidiness, ensure that it resides in the Assets Textures folder. In the Hierarchy panel, unfold the Ethan object. Click on the triangle and select Ethan Body. In the Inspector panel, unfold the Ethan White shader by clicking on the triangle icon to the left of Shader. Select the Ethan Zombie texture from the Project Assets Textures folder. Drag it into the Albedo texture map. It's a small square just to the left of the Albedo label under Main Maps. In the Hierarchy panel, select Ethan Glasses and uncheck it to disable glasses in the Inspector panel. After all, zombies don't need glasses. What did you say about this? That's a lame-looking zombie. Well, maybe he's just recently turned. Go ahead and make a better one yourself. Use Blender, GIMP or Photoshop and paint your own, or even import a whole different zombie humanoid model to replace Ethan Body itself. Now, build the project and try it in VR. We're looking from a third-person perspective. You can look around and watch what's going on. It's kind of fun, and it's pretty interesting. Cool! In this video, you learned about Ethan the Walker, where our character Ethan was made artificially intelligent and was made to roam around. Great!